Hello, hello. Let me know when you can see and hear me, please. Hi. Happy Friday. Hello, hello. Hi. Hello. Who's here? Hi, Man. Hi. How are you? Who else do we have? I know for lots of you it's your last day of school. So if you're joining me on your last day of school, shout out to you. And if you're already on holiday and you're joining me, shout out to you even more. If you are on TikTok, reminder, lovely Iman. If you're on TikTok, reminder that I'm only looking at the chat over in YouTube. So if you go to the link in my bio on TikTok, then you can come and join in the fun over here. Lovely Iman. I am well. I'm looking forward to the holiday. Hi, Redeemer. Hi, Chinwendu. Hello, hello. Okay, yay. Let's get started. Let's get started. Today's mini drop-in session is all about Redox, and we're keeping it simple with like the foundations of Redox, so like the year 12 Redox. I've called it Redox 1, which is what it's typically called in why can't I speak in EdXL, but it's called Redox in most of your exam boards as well. Hi, natural scientist. I am well. How are you? Thank you for joining. So let's get started. Let's do a reminder first of oxidation states. Okay, because essentially, what is what is an oxidation state? An oxidation state, that's a hypothetical charge of an atom if all of the bonds were ionic. Okay, and the reason that we use oxidation states is that we can clearly track the gain and loss of electrons, so reduction and oxidation. Because in some reactions, the loss and gain of electrons is really obvious. Okay, well, hopefully. So if we look at this first equation up here at the top, what species has lost electrons? Hi, Michael. What species has lost electrons in this first equation? Okay, yeah, absolutely, Chinwendu. This one, the second one should be in your like long-term memory. Absolutely, Michael. Lovely. The magnesium has lost electrons, specifically 2 electrons, and then the copper 2 plus has clearly then gained those 2 electrons. Lovely. So that's really obvious. But if we have something like peroxide disulfate forming sulfate ions, it's not quite as straightforward to tell what's lost or gained electrons if we don't know anything about oxidation states. Okay, so let's make sure that we know the rules for oxidation states. Again, we're going to do like a whistle stop tour. If you want me to stop and slow down for any of these, please, please, please let me know in the chat. Okay. And also, quick reminder, any year 13s here that are not on the annual MES course already, then the Easter revision course, which will be 1 week of the Easter holidays, will essentially be doing exam practice, like running through the entire course. So if you have not signed up yet, then the link is in the description of this video to sign up for the Easter revision course. Okay, and you can find out more about it in the link. So if you're already on the annual MES course, you don't need to worry about it. It's included. If you are not, then make sure that you sign up. Even if you're not coming to regular sessions, just coming to that Easter course. Okay, so let's look at the oxidation states, but the rules. First of all, atoms in an element, so if it's just the element by itself, then the oxidation state has to be 0, because even if the bonds were ionic, if they're both the same element, then they would technically have the same share of electrons. So whether that's a metal or whether that is a non-metal and a diatomic molecule even, the oxidation states for all of these are going to be 0. The next simplest one, if we have a simple ion, then the oxidation state is the same as the charge. So for our sodium ion, can you give me in the chat, please, the oxidation state? And you might as well give me the sulfide ion as well while you're there. What are our oxidation states? Again, if there are any answers coming through on TikTok, make sure that you go to the link in the bio so you can come and tell me the answer over here. Okay, so Michael, you're not wrong, but you're also not right. Okay, because when it comes to oxidation states, by convention, we put the sign before the number. So for a charge, it would be 1 plus, but for an oxidation state, we say +1. Okay, lovely. And then for our sulfide ion, lovely. Thank you, Michael. Great, -2. Okay, now let's just keep going. One step, one step, one step up. Rule number 3, the oxidation states of the atoms in a neutral compound must add up to 0. Okay, so if the overall charge of the compound is 0, then if we combine the individual oxidation states, that should add up to 0. Hello, I'm assuming Sabiha? Hi, welcome. So for sodium oxide, sodium is in group 1. So we know it would have an oxidation state. Okay, lovely, Sabiha. An oxidation state of +1. And there are 2 of them. So they're contributing +2, which means that the oxygen must have an oxidation state of -2. Okay, so that overall, the oxidation states will add up to 0. Wonderful. Final rule, I don't know why it says 2, pretend that says 4. The oxidation states of the atoms in a complex or a polyatomic ion must add up to the total or the overall charge of the ion. So for example, if we've got sulfate, and just as a quick sneak peek, oxygen almost always has an oxidation state of -2. So if the oxygen has an oxidation state of -2, there are 4 of them, so they're contributing -8, and the overall charge of the ion is 2-. So with that in mind, what must the oxidation state of the sulfur be to make sure that the overall charge still adds up to 2-? Who's got it? Who's got it? Quick maths. What do we need to add to -8 to give us -2? Absolutely, Aman. Oh, no, almost, not -6, because -6 minus 8 would give us -14. So it has to be +6, because +6 minus 8 gives us -2, which matches the charge of the ion. Okay. Should we do another example of that? Let's do one more example. Let's do chromate. Oh gosh, now oh gosh, do I even remember? Actually no, that's basically the same. Let's do, oh my gosh, ions, chlorate, ClO3 minus. Okay, so again, we can use the oxygen as our starting point. Oxygen will have an oxidation state of -2 because it's -2 99% of the time. There are 3 of them, so contributing -6. So then what must the oxidation state of the chlorine be in order to give us a total charge of the ion of -1? Wow, that's a lot of words. Amazing. Natural scientist, shout out you. +5. Perfect. Lovely. We're going to do some more practice of these after I've given you the last set of rules and exceptions. Okay, but any questions at any point, please, please, please let me know. Okay, so, oh, okay, bonus rules and the exceptions. So, oxygen, as I mentioned before, most of the time it's going to be -2. So we can typically use oxygen as our like our foundation to compare all other oxidation states against. However, you need to spot where, lovely Chinwendu, where oxygen is in a couple of different environments. So in peroxides, like hydrogen peroxide or sodium peroxide, the oxygen actually has an oxidation state of -1 instead. And when oxygen is combined with fluorine, because fluorine is the most electronegative element on the periodic table, the fluorine is always going to have its oxidation state of -1. There are 2 of them, so contributing -2, which means that the oxygen must have an oxidation state of +2. Okay, so look out for those exceptions for when the oxygen is not going to be -2. And of course, when it's an element, it's going to be 0, but that's the same for everything. Okay. Similar with hydrogen. Hydrogen in most compounds, so again, like 99% of the examples that you're going to see, going to have an oxidation state of +1. except when it's combined with metals in metal hydrides, where it has an oxidation state of -1. Okay, so for example, sodium hydride, the sodium will form a 1+ ion, therefore the hydride must be -1. Okay, let's put that into practice. We're going to assign a whole bunch of oxidation states, so I'm going to need you to tell me the answers, please, in the chat. Thank you. So let's start with HBr. Out of the H and the Br, which one are we going to start with as our baseline? Which one are we starting with? Lovely, natural scientists. Great. We can start with our hydrogen, which would have an oxidation state of +1. Great, Michael. Lovely, Sabiha. Which means because the total compound, the overall charge of the compound is neutral, so the bromine must be -1. Great. Let's go over to the water. Again, feel free to just flood the chat with your answers. Doesn't have to be in order as long as everything is labeled. Okay, so for H2O, natural scientist, amazing. Hydrogen +1, oxygen -2, and we know those as our rules anyway. Lovely, Sabiha. Let's go to our sodium chlorate, or one of our sodium chlorates. Lovely, Aman. For NaClO, where could we start? Where could we start? Lovely, Michael. The oxygen we know is going to be -2. Where would we go next? What would be a sensible place to go next? Absolutely, natural scientists. We want to go to the sodium next. Sodium is in group 1, so it would form a 1+ ion, or +1 ion. Yeah, +1 ion. Lovely. And so the chlorine is going to make up the difference. And as natural scientists has told us already in the chat, fantastic. In order for the overall charge to be neutral, the chlorine must have an oxidation state of +1 as well. Yeah. So that overall +1 +1 -2 gives us 0 in total. Okay. Lovely. Let's go to our polyatomic ions. So starting with the phosphate ion. Where are we starting? And how are we going to use that to our advantage? What do we know already straight off the bat? Ooh, not necessarily, Sabiha. Not necessarily. We know about the oxygen. Okay, we know that the oxygen has an oxidation state, absolutely, of -2. A polyatomic ion, Chinwendu, is any ion that's made up of more than one atom. So your sulfates, your carbonates, your nitrates, ammonium, etc., those are all polyatomic because it's not just like Cl- or P3-. Okay, hi, Mr. Magic. What a great name. Hi. Okay, so the oxygen is -2. There are 4 of them, so they're contributing -8, which means, lovely natural scientist, lovely Aman, the phosphorus must be +5. Okay, make sure that we're really careful though. If you were asked there for the oxidation state of the oxygen, we're not going to say -8. Okay, the oxidation state of the oxygen is -2. We only do the ×4 to get us to -8 to figure out what's happening with the other thing so that everything can cancel and balance out as it needs to. But the oxidation state is not -8. The oxidation state of each oxygen is -2. Okay, last one of our favorite ions. Well, one of my favorites anyway. It comes up so much in A-level chemistry and it looks really pretty too. It's a really nice deep purple color. Feel free to just chuck your answers into the chat. Wonderful. Great, great, great. Lovely. The oxygen we know is -2. There are 4 of them, so contributing -8. So the manganese, wonderful, must be +7 is what I meant to say. Okay. Oh, Mr. Magic, we are focusing on redox today, but if it's a quick question, then I'll answer it. Okay. So type it. And if it's, simple enough for me to explain, relatively quickly, then I absolutely will. Okay, lovely. So we can assign oxidation states, and that helps us track oxidation and reduction. Let's remind ourselves, Gibbs energy, Mr. Magic, tells us whether a reaction is going to be spontaneous or feasible at a particular temperature. So whether or not it will happen without any external input. And if Gibbs free energy is negative, then that reaction is feasible and will just take place spontaneously. If Gibbs free energy is positive, or delta G is positive, then that means that the reaction is not feasible or not spontaneous. Okay, and there are a few different ways that we can calculate Gibbs. Again, I think we should have a whole lesson on Gibbs, okay? But hopefully that is a good summary for you. Lovely. Okay. Yeah, we absolutely use oil rig at A level. There are a few different definitions for oxidation. The simplest one, which is what we saw at GCSE the most, oxidation, we can say gain of oxygen, not O2, but just gain of oxygen, with reduction being loss of oxygen. I've seen oil rig from Iman and Michael and Chinwendu. Oh, and natural scientist. Lovely. Oxidation is the loss of electrons. Reduction is the gain of electrons. There's another one that links directly to, this is A level, yes, Sabiha. There's another one that links directly to our oxidation states. What might happen to an oxidation state during oxidation? Oxidation state or oxidation number. Yeah, absolutely, Sabiha. I would say what we're going to do. Yeah, actually, you know what, Sabiha? Absolutely. Yeah, you can. For oxidation, what might happen to the oxidation number? Go up or go down, increase or decrease. If we're oxidizing something, the oxidation state will, lovely natural scientist, oxidation number increases. If something is oxidized, its oxidation state is going to go up. And if something is reduced, then the oxidation state or oxidation number decreases. Okay, so you'll be asked about these in different contexts, right? In some questions, they might say, explain in terms of oxygen at GCSE more often than not, whether this is reduction or oxidation. At A level, they'll typically ask explain in terms of electrons or explain in terms of oxidation state. Okay, absolutely, Aman. We're gonna do a couple of examples. Don't worry. Okay, we're coming on to the examples on the next few slides. What is redox though? What is redox? I'll start you off. Lovely. Ooh, great. A reaction in which both oxidation and reduction or reduction and oxidation are taking place. Huh? I wrote oxidation state in both. Yeah. Okay. So oxidation state increases for oxidation state decreases for reduction. Okay, let's look at this. Let's look at all of these definitions. Well, maybe not necessarily this first one. No problem, Chinwendu. Not necessarily this first definition. I think we'll leave this definition for organic chemistry and GCSE, and we'll focus on the electrons and oxidation state, which is what we see the most at A level. Okay, so we can track this using half equations. If we've got Cl minus going to Cl2, before we've actually even written the half equation, we should be able to spot whether this change is oxidation or reduction based on the oxidation states, okay, or oxidation numbers. So the Cl minus, what's the oxidation state there of the chloride ion? Cl minus has got what oxidation state? Oh, hang on, before we start balancing, Chinwendu, you're absolutely right. But yep. So at the moment, just -1. And the Cl2, so when it's just in its elemental form, has an oxidation state of 0. Okay. What has happened to the oxidation state or the oxidation number? Has it increased or decreased? Increased or decreased? Anyone? From -1 to 0, lovely, Aman. Oxidation number increased, which means this must be lovely. This is oxidation. Great. Now, actually balancing this half equation, that's going to show us how the electrons have been, well, it's oxidation, so loss of electrons. So first, Chinwendu, you're way ahead of us. You're absolutely right. We want to start by balancing our species, our elements. So we need 2 Cl minuses, and then we can balance the charges with our electrons. So we have currently a charge of 2 minus over here, a charge of 0 over here. So that must be 2 electrons on the right-hand side. Okay, lovely. So now we can explain this oxidation also in terms of electrons. We can see that electrons have been lost. So we can even say 2 electrons lost, therefore oxidation. Okay, so we've explained this in 2 ways, in terms of the change in oxidation state and in terms of the loss of electrons. Okay, let's do the next one. Oxidation states here are really straightforward, so I won't necessarily ask you, we'll just speed ahead with this. Because if they're simple ions, oxidation state over here +3, oxidation state over here +2. What's happened to the oxidation state or oxidation number? Lovely, decreased, therefore must be reduction. Okay, and you're absolutely right, Chinwendu. If we, in terms of balancing this half equation with electrons, that would mean we'd need to add 1 electron on the left-hand side to balance the charges. And again, we can see this is also reduction in terms of electrons because 1 electron gained, therefore reduction. Okay. Oops. Let's just complete our sentences from Cl minus. From Okay. How do you know which side to put the electrons on? So, Iman, the simplest way that I like to think of it is just in terms of balancing the charges. You put the electrons on whatever side you need to put those electrons on to make sure that the charges cancel, balance out. So at the beginning, we had +3 on the left, so 3 plus on the left and 2 plus on the right. So we need to bring that charge down by 1, so we're adding 1 electron. Okay, or if you're more of like a memory recall type of thinker, then you can think of it as reduction. The electrons go on the left because we're gaining electrons, so the electrons are a product, are a reactant, sorry. Okay, so like A plus B, the electrons being a reactant. Whereas if we're losing electrons, then those electrons are a product, so they go on the right-hand side. Okay, lovely. Let's do some trickier half equations where we've got some polyatomic ions. Now, there are a couple of ways to balance these. The way that I typically teach to balance it isn't necessarily my favorite way in terms of understanding, but I think it's the best way for anyone that is still maybe a little bit confused about oxidation states. Because even if you've got no idea how to assign oxidation states, you'll still be able to balance these half equations using this approach. Because it's all just about like numbers and balancing instead of having to understand oxidation states first. Okay, so again, if you have another way of doing this and you're always getting it right, keep doing that. Okay, I'm not going to tell you to stop. I used to do it a different way for a long time, but this way you can get it without knowing much else. Okay, so what I would do first, so we will add some H pluses omicron, but not yet. Our first step is to balance our elements, our species. So the manganese, the species that's being oxidized or reduced. At the moment, there's one manganese on each side, so we don't need to do anything there. Then, because in this manganate ion we have oxygens, we need to balance those oxygens using water, because this is all happening in aqueous solution. So we've got 4 oxygens on the left, so we'll now add 4 waters on the right. Lovely Chinwendu. Okay, so balancing our oxygens with water. But now we've added some hydrogens. Now, in AQA, we can assume that we're always in acidic solution. In other examples, there are a couple of examples for alkaline, but I think we might have to save that story for another day. Let's stick with acidic for now, because that's the most common example that you'll see. So because we're in acidic solution, we can balance the hydrogens with H plus ions. And you're absolutely right, natural scientist. We will need 8 H plus ions. Okay, typically it will be sulfuric acid that we use, but the counter ion doesn't really matter. The key thing with the balancing is the H plus. Okay, so 8 H pluses to balance the 8 hydrogens on the right-hand side. Now all of our elements are balanced. Now we need to balance the charges using electrons. So I would look at the total charge on the left-hand side, which is -1 from the manganate, and then 8 plus from the hydrogen. So that gives us 7 plus, or +7. On the right-hand side, we've got 2 plus from the Mn2 plus, and the water is neutral. So in order to balance those charges, Chinwendu, you're absolutely right, we will need 5 electrons on the left-hand side, because we need to subtract 5 from 7. Oh my gosh. We need to subtract 5 from 7 to get down to 2. Okay, and now we're done. Again, we could have done this in terms of oxidation states instead. We could have identified that the Mn oxidation state was +7 over here, and then +2 over here. So we know that we're adding 5 electrons. Okay, so it works whether you use it just in terms of the charges or whether you do it in terms of oxidation states. Okay, Iman, trust me, it will become so much simpler once you've done practice. It's just about following the steps. The +7, so we just needed the charges to cancel. We had 7 plus on the left, so -1, and then 8 plus, which gave us 7 plus. On the right-hand side, we had 2 plus from the Mn2 plus. So exactly, Chinwendu. So we needed the charges to be the same on both sides, which meant adding 5 electrons, because electrons are negative. So if we add 5 of them, so 7 plus and then -5 gives us 2 plus. Okay, Iman, we add water because this is happening in aqueous solution, which means that there's water around. And because we had oxygens in our manganate ion, we needed waters to balance those oxygens. Okay, let's do another example. Hopefully it will get clearer and clearer the more that you do. Okay, let's do this one. And I think this might be the last one because we are coming to the end. Right. So VO2 plus going to V3 plus. Our first step, we'll check that our vanadiums are balanced. They already are. So now our next step is to balance our oxygens using water because we are in solution. How many waters are we going to add and on which side? Oh, Misbah, good question. Oh, good question. I would balance the oxygens because typically it's the oxygen that's changing oxidation state, because it will typically be from -1 to 0 or -1 to -2. But whichever one you do, it will end up kind of working itself out. Okay, absolutely. Thank you, Iman and Chinwendu. 2 waters on the right-hand side to balance our oxygens. Next step, balance our hydrogens using H plus. How many H pluses and on which side? Oops, spoiler. Can you see my pen? Lovely. 4 H pluses on the left. Lovely. And now we can balance our charges using electrons. At the moment, the total charge on the left-hand side is 5 plus, right? 1 from the VO2 plus, and then 4 from the H plus. On the right-hand side, the overall charge is 3 plus. So how many electrons? Oh, not 7. How many would we need to balance those charges? Not 6 to get from 5 plus to 3 plus? Absolutely, just 2 electrons on the left-hand side. Great. That shows us straight away that this is reduction because the VO2 plus has gained 2 electrons to be reduced to V3 plus. Again, we could have also spotted this with our oxidation states. The oxidation state of the vanadium over on the left is, what is that, +5. Over on the right, +3. So we knew we needed to add 2 electrons. Amazing, Iman. Great. And when we get to this when do we do this? In year 12, for our year 12 course, we do this in January. So hopefully this will be like a nice head start where you'll feel like nice and comfortable when we do it again for a full lesson. Remember our oxidation states, oxygen is -2. There are 2 of them, so contributing -4. The overall charge of the ion is 1 plus, so +5 -4 gives us 1 plus. Okay. Ooh. Do you want to do one more or do you want to go? You tell me. Actually, I'll know if you like the video, then I'll know that you want to do one more. And if you don't like the video, then I'm going to go eat my lunch. Quantum chemistry we don't do at A level. Okay. Oh, I love to see Jay. That's wonderful. Yay. Okay, one more, but there's still only 1 like on this video. What's going on? Maybe I just need to refresh. I need to see those likes going up. Okay. I'll start to write the question, but I want to see that number change. Oh, there's 6. Okay, I take it back. Thank you, Sabiha. Mine just isn't refreshing. Let's do I like this one. Let me give myself some space. Okay, good to know. Thank you, Jinwendi. Okay. First step. I noticed there are no rules here, so now let's start to get into the process. What should we do first? What should we do first? Lovely. I'm Rich in Mendu. Before the waters, there will be 7, but we need to balance the chromiums first. There are 2 on the left, so we'll put 2 on the right. Okay, and then you're absolutely right. We'll need 7 waters on the right-hand side to balance the oxygens. Now, lovely natural scientist will now need 14 H pluses on the left to balance the hydrogens. Finally, what should we look at to figure out our electrons? Again, there are 2 ways we can figure out the electrons. You can pick your favorite way. Anyone? Okay, so Chinwendu, let's see if you're right. 6 on the left. Let's see. Currently on the left-hand side, we have a overall charge of, 2 minus 14 plus, which gives us 12 plus. On the right-hand side, we've got 2 times 3 plus, so 6 plus. So you're absolutely right. We would need 6 electrons on the left-hand side to balance those charges. Okay. Before we go, just to make sure you've really, really got this, can you please tell me, as your parting gift, as your Christmas present to me, what the oxidation state is of the chromium in the dichromate ion? Hi, Samir. Oh, so the oxidation state doesn't increase, but I just want the oxidation number. What's the oxidation state? Again, use the oxygen to help you out. Is that a 6 plus or a 6 minus, Chinwendu? Or a plus 6 or a minus 6? This is A level, Samir. Okay, Chinwendu was saying plus 6. Do we agree? I'll give you a hint. You should agree. I agree. Okay, so lovely, Jay. We can use the oxygen. Oxygen has an oxidation state of -2. There are 7 of them, so that's contributing -14. Okay, the overall charge of the ion is 2 minus, which means that the chromium must be contributing +12 to give it to -2. But there are 2 of them, so each chromium has got an oxidation state of +6. Okay, so we're going from +6 to +3. Our oxidation state, wow, has decreased, which means this must be reduction. And we can also see that because we've gained electrons. Yay. Okay, lovely, Aman. Okay. Is the 6 from the electron thing? Yes. If I'm understanding your question correctly. I think that from what you're asking, I think that my answer is yes. Okay. Oh gosh. Okay. Yay. Oh my gosh. Before we go, I want to show you my Christmas jumper. Okay. Feel free to leave if you don't want to see it, but you'll really be missing out. And to be fair, the reason I didn't wear it today is because the green screen will kind of block out most of it. Yeah. Oh yeah, Aman, you saw it. Okay. Pretend that it's green. Pretend that it's green. Can you even kind of? It's the periodic table. Isn't it the best thing ever? Makes me so happy inside. Right, Jay? Oh my goodness. Oh, chemistry. Oh, chemistry. Wonderful. Thank you. I really wish I could wear it, but I had to at least show you. Okay, lovely. Have a wonderful Christmas break. Have a happy new year, and I will see you in January. For some of you year 13s, I will see you this afternoon where I'm gonna show you the jumper again because I'm not excited and you haven't, and most of you wouldn't have seen it yet. Okay, have a lovely holiday. Okay, lovely natural scientist. Great. So, oh yeah, you'll see me on TikTok doing some more videos over the holiday as well. Okay, there won't be a video, I don't think, on Christmas Day because I think, we'll give you a bit of a break. But yeah, see you soon. Yay. Bye. Well done. Well done.